Hi, today in this video, we're going to talk about composition of functions. The title of this section, which is section 1.4 of the book, is building functions from functions. So what could we do with those functions? What operations could we do with them? The first slide is pretty much a prerequisite where we all know we can add functions, subtract, multiply, and divide. So I'm going to go ahead and complete the first part. We're going to add f of x and g of x. And you guys know where we can combine like terms. So 2x plus a 3x, a 5x. And negative 3 minus 1 is a negative 4. I added a linear function and another linear function, and I got a result, a linear function. Now with subtraction, 2x minus a 3 minus a g of x, I'm not going to forget my parentheses. And I know a negative next to the parentheses gets distributed. So it's 2x minus a 3 minus a 3x and plus 1. And now I combine like terms. 2x minus a 3x is a negative x, minus a 3 plus 1 is a negative 2. And this is my new function, which is the result of subtracting functions. Now, multiplication, and this might take a little bit more space, so I'm going to do the multiplication right here. 2x minus a 3 into 3x minus 1. And what we do is we FOIL those two functions, and then we combine like terms. I'm not going to complete that because this is not our objective. This is just a prerequisite. The last one, division. So 2x minus a 3 over 3x minus 1. And there's nothing I could do about it. So this is a new rational function. And just this is a misconception that I would like to address. I cannot divide this into two portions. I can't say, oh, it's 2x over 3x minus a 3 over negative 1. This is incorrect because remember, this is a common denominator. So the correct way of dividing this, and you don't have to, just showing you each of those terms on top on the numerator get the common denominator. So this is a correct way of splitting the fraction. This is not a correct way. Now, in your homework and in your application, you're going to see examples like adding functions like this. This is f of x, this is g of x. Adding them or subtracting them. And you would say, okay, what do I do next? Actually, nothing. Because I cannot combine a linear with a square root. I can't do anything about it. So if I say f plus g, and this is f of x, and this is g of x, so f plus g will just be 2x plus the square root of x minus a 3. Or I can still keep it in the same order, it doesn't matter. So this is just a tip for part of your application that you're going to be working on. If there's no like terms to combine them, then there's nothing else to do. Our main objective, which could be a new objective, is composition of function. So now I'm not adding, I'm not subtracting, I am combining them. And I would say this is an example of, we use the machine analogy. For example, if you are producing any type of product, and you perform two operations on that product. You may be like, I would say like Pepsi. First, you have to fill the bottles and then you cap them. Those are two operations. Those are two machines. This product is going to go through two different machines, one after the other, so you can get the final product. Similarly, you're going to apply f of x and the g of x. So you're going to look at the function which is applied first. So we're going to read this as f of g. And this is a small circle which says composition of functions. So small circle, and we read it f of g. It's not a 0, it's not a dot, it's f of g. And you need to know how to rewrite it as a f of g of x. And this simply means take g of x and put it inside of f. And when I say inside of f, I'll put it inside the input, which is x. So I'll read it f of g of x. And this is, which means I'm applying both functions to the input. I am, again, keep in mind, I am filling the bottles with the Pepsi and then capping them. Filling the bottle, then capping them. Two different machines. So you need to understand that F comes first, then G. But this means take G and put it inside F. So I'm going to take G and put it inside of F in the input. So I'm going to take X away and I'm going to put G of X, all of it, and I'm going to complete the function. And this would be F of G of X. We have two more examples. So for this example, I'm going to do both because you could be asked to do F of G of X and you could be asked to do G of F of X. And also never forget your parentheses, which means you're using two machines. This could be written as F of G of X, which means take G of X and put it inside F in the input. So I'm going to take the X out and I'm going to put square root of X. And I'm still going to apply the machine, square minus 1. A square eliminates the square root and this is X minus 1. If I were to do G of X, it's G of F of X. So take F of X and put it inside the G. So I'm going to take all F of X and I'm going to put it inside the G function. Where? In the input. So I'll take X out and I'll put X squared minus 1. Another example, F of G of X. It's very important to memorize and understand the notation. I'm going to take G. I'm going to put it inside F in the input. So 2 multiplied by, this is G of X and minus 3. And I can't do anything about it. I can't combine any like terms, so I will just keep it. G of F of X is G of F of X, which equals, you take F and put it inside of G. So this is the G function. It has an X. I'm going to take it out and instead I'm going to put all F function, F of X. And there's a plus 1. So all what I can do is 2x minus 2. And this is the new G of F of X. Now, sometimes in the book problems that you are asked to complete, which are page 116, numbers 1 through 4, and then those would ask you just to do addition, multiplication, and subtraction. So just like our first slide right here. And then you're going to do 11 through 14. I asked you here to ignore the domain because I'm not going to ask you to find the domain now. I'm just going to ask you to find the composition of function. And this is asking you specifically for f of g of 3. So it's asking you for a composition of function for a very specific input. So I'm doing right here, this is number 11, just to give you a quick tip. So I know this is f of g of 3 instead of x. I was working in general in the previous examples. Right here, we'll make it a little bit more specific. So what I'm going to do, this means apply g first and then f of x. And if you look at g of x in that example I'm working on, it's x plus 1. So it will be 3 plus 1 which is 4. So I'm going to do f of 4. And f of x is 2x minus 3. So I'm going to substitute 4 in f of x. I'm going to get 8 minus 3, which is 5. So again, let's recap. This notation, so they gave us f of x to be 2x minus 3. And they gave us a g of x in the example 11 to be x plus 1. And they're asking us not of g of x in general, but more specifically with a specific input. So I'll rewrite it in that notation. And I know I'm going to start with the inside. So I'll apply g of 3 first. So I'll plug in 3 in g of x. So 3 plus 1 gives us a 4. Now this 4 is going to be the input of f of x. So I'll apply g first, inside, then outside. Then f of 4, which means plug in 4 in f of x. 2 times 4 is 8. And 8 minus 3 is 5. Very important misconception to take care of. This notation does not mean f multiplied by g. So I'm going to write it right here. This in any mean does not mean multiply f by g. No, it means apply g first to this input. Once you're done, take the result and put it in f of x. If I were to ask you to multiply them, then this would be the notation I would use. F multiplied by g with the dot in between. But if I give you this means start with G, apply it, and then the result, take it and put it in f of x. If you are given a specific input, like this case, it will be easy to work with numbers. If you're given a general input like x, then you will just be working with functions. And I hope this helps.